Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. This is primarily for CP Physics. This is a handout called the Electroscope, Charging by Grounding. And I have a copy of it here. So it is a sequence of images with a brief instruction on the left, image of the electroscope in the middle, and on the right, you're supposed to fill in your observations about what you see going on and explanation about what's going on. So let's get started with it. This device is called an electroscope. It's a can. On top of it is a metal plate. It's got a little insulator right there to keep it from touching the outer wall of the can electrically. Going through that insulator is like a screw. Inside the can, there's this bracket that is shaped to hold a little cradle in it. And resting on the bracket is a piece of aluminum foil wrapped around a cardboard tube. And it has a pin stuck through it to try to have it balanced so that it can swing relatively easily. And it's just resting there on the bracket. You could make one of these at home yourself when you say, well, do I need a can? Actually, you can make it much more simply than what's shown here. If you were to go take a strip of aluminum foil and cut it and then fold it and hang it on a paper clip, you've essentially done the same thing as what this thing is showing here. And usually we hang it inside a glass. So you touch the top of the paper clip and it'll do the same thing that I'm going to demonstrate here. So what's going on is metals are conductors of electricity. Electrons can easily flow in a conductor. They don't move in an insulator like this little isolator here. And I'm going to try to show you how to charge this object, put some electricity onto it. So here's the trick if it works. Up in the first panel, it says Electroscope. And really, that's the letter N was cut off when I scanned it in. So it's neutral electroscope. In the middle panel is the drawing of what you see right now. And you're going to have to go by direct view here because the camera is just not set up to show this, the right orientation. The arm, I'll call it, is free to swing. And right now it's just vertical. So my own comment to fill it in for you is the arm is vertical. There's no net electric charge on the electroscope. And I don't know if you can read the very fine print here, but it says, show in each picture how it is positioned. Okay, so the first one is done for you. Now, the next frame says, bring charged object near. And it shows the electroscope. The charged object would be a PVC pipe. And the arm is not drawn. So the arm, which is free to turn, is what you need to pay attention to. So and I guess, yeah, okay, so I'll do it in this order. Here's a piece of PVC pipe, here's some wool, and when I rub it rather hard, I'm scraping electrons off of the PVC pipe and onto the wool. So the wool is becoming positively charged, and the PVC, I'm sorry, I said that wrong. The wool is becoming negatively charged because it's gaining electrons, and the PVC pipe is becoming positively charged because it's losing those electrons to the wool. So here's number 2. I bring my charged object near the electroscope and voila, you see the magic trick. Look, see, it's not me. As I bring this charged object near the top of the electroscope, but not touching it, you can see that the arm starts to swing away from the bracket that it's on. Okay, so let's just pause and fill that one in. How should I draw the arm in this situation? Well, I should show that it tilted, right? So too bad I have terrible drawing skills. Good thing you have excellent drawing skills. And now the part is you're supposed to explain why it did that. So let me, you should pause and think about that and then play. But here comes the explanation right away. The PVC pipe is positively charged. So I'm going to draw several plus signs inside the PVC pipe. There they are. Now, electrons are the only charges that are free to move around. Protons are stuck in the nuclei of the atoms. Electrons are on the outer cloud, and they're available to move. So what's going on here is the electroscope was neutral, and it's still neutral because no one ever touched it, right? It's neutral right now. And when I bring this positive rod near it, it's still neutral because nothing has touched it. But what makes it swing is the flow of electricity inside this contraption. So electrons look at the positive rod up here and say, oh, opposites attract. I'm attracted to you. And the electrons up here are just so happy. They're, oh, please let me go and get onto this PVC pipe. They want me. They need me. I want to go there. And the electrons way down here say, hey, what about us? I see you guys need more electrons up there. Let's go up there and maybe we can get onto the PVC pipe. So what happens is the electrons leave the inside of the can and go up to the top of the can. So therefore, as electrons pile onto the top of this plate here, all trying to get to this PVC pipe, what is the charge on the plate now? It's not neutral anymore because electrons have come up from the inside. So this has extra electrons up here, and I'm drawing some minus charges, and it's not going to be as many as the pluses here, right? So this method of charging is weaker than what you start with. Now they left down here, and they left from the arm, which is free to swing, and they left from the bracket. They left from the entire neighborhood. So what's left behind is a positive charge on the bracket and on the arm, because these electrons had gone up to the plate. The whole thing overall is still neutral. So for every plus that I draw down here, I should draw a minus up there on the plate. So what happened when I bring charged object near? You would have to write some explanation, and you're going to explain what I just said to you verbally. You're the ones who get to write it down, right? I could say electrons flow up onto plate. And so why does the arm swing? Because like charges repel. And what's down here inside the can under this condition is an absence of electrons. They've left the arm, they've left the bracket, and now they're like charges here on the inside. They don't know what's going on up there at the top anymore. They're just saying, look, down here, these are like charges. I hate like charges. Like charges repel each other. And so the arm fights to get away from the bracket, fighting even against gravity until the force of gravity matches the electrostatic repulsion force, and then it reaches this equilibrium angle here. Okay, so that is the explanation for frame number 2. There's more. Number 3, ground the electroscope. And it says touch, which means touch the top with your hand. Touch the top with your hand. So let me explain. Mother Earth is considered to be an infinite source or infinite sink of electricity. So when we ground something, that means we are electrically connecting ourselves to the entire planet, figuring that, well, if I have extra electrons and I need to get rid of them, give them to Mother Earth. Or if I need electrons, take them from Mother Earth. She's so big, she won't miss them. And she won't care if you give her some extra ones. Because overall the balance for the planet is going to be neutral, right? So I'm going to substitute for Mother Earth. If I were to take a grounding wire out of the outlet, and don't try this at home, and touch it, I would be doing exactly the same thing as it says here in step 3, ground the electroscope. However, we don't really want you students foolishly messing around with the electrical outlets unless you're under the supervision of a trained professional, and you're not. So I'm going to substitute for Mother Earth. Yes, yes, I've been a substitute teacher before, so might as well be a substitute Mother Earth. And so what that means is we're going to treat my body as a source of electricity if necessary. Either I can give it electrons or I can take electrons away, and they'll go onto my skin and it'll be okay if I have extra electrons. So here we go, step number 3. And by the way, it's going to be immediately followed by step 4, and then immediately followed by step 5. So I'm going to do the entire sequence all at once here. I have this electroscope. It's currently neutral. I charge up a positive PVC pipe. I bring it near, but not touching the electroscope. You see it swing. Now I touch the plate of the electroscope. Now I take my finger away, and now I take the rod away. And it didn't really work correctly. I'm wondering if I should shut this off and do this again. No, I'm going to try it again. So first, I'm grounding it by touching it. Next, I'm going to charge up this PVC pipe because it's always good to have it well charged. Then I bring it near, it swings, I touch the plate. Let's say I go like that. Then I take my finger away, then I go like this. Okay, very crude, but it worked. Yeah, okay, ever so slightly, that was successful. I'm going to try it one more time. Maybe I can get a little bit more obvious result. So it's neutral. I touched it for a moment, took away any extra charge it had, or gave it electrons if necessary. Charge this thing up. I bring it near, it swings. I touch the plate. I take away my finger, and I take away this. Doesn't work very well. Nonetheless, you expected to have the correct answer from the textbook as a result of this. So I'm going to explain to you what should happen, and then you know what to look for. So the magic trick really is that what you saw. So here's the explanation of how it should have gone. When I bring the charged rod near, the electrons float up here to the top, saying, oh, I want to get to this thing. When I touched my finger, first times I touched it up here, and then I wanted to make more obvious. I said, okay, obvious. I touched the bottom of the plate. So what's going on is I'm touching a positively charged plate with my finger, right? And I'm touching that positively charged plate. Well, acting substitute for Mother Earth, I'm grounding the top of the plate. I'm giving it electrons actually in this moment. And so it has electrons from my finger on the plate now. And the electrons had come up from below, said, oh, like charges, no need for me to be here. So they go back where they came from inside the plate. And so now the arm and the bracket are vertical once again. I take away my finger and it removes the bridge. So no longer can charges flow. And when I take the rod away, now the rod swings, the arm swings. So it's kind of working. You're supposed to explain that and understand it completely. So let me guide you along a little bit. In the third frame, the positively charged rod never touches anything directly. So it just stays positively charged rod. Same thing on the next frame. We could just jump right down and say, well, the positively charged rod is still the positively charged rod. It never changes. Still positively charged. What happened here? The electrons in frame 2 had gone up to the plate, making it positively charged. When I touched it with the fickle finger of fate, electrons went from my finger onto the plate because just like the ones that were inside the electroscope, the electrons in my finger said, oh, you need electrons because this is a positively charged area here. I give you some electrons. And so electrons go onto the plate. Now it believes it is neutral because the whole electroscope. Let me clarify that. So this positive region receives electrons, making it hard to describe. So I'm going to draw the arm as being vertical. And the only condition under which an electroscope is neutral on the inside is if there is no net charge here. So misconception by students is to say, oh, what happens if I do a negative charge instead of a positive charge? And the answer is there's no difference visually. It will have identical behavior. So if I'd done this with a negatively charged rod, it will still have exactly the same visual behavior. It's just that the plus and minus signs would be flipped. So for it to be vertical means it has to be neutral in here. So I would draw a checkerboard pattern. Let's go plus minus, minus plus, plus minus, minus plus. So it's neutral in there. And up here, it thinks it's neutral. It's being influenced by the positive charged rod nearby, but really it has extra electrons from my finger. So what I just crudely sketched on this sketch is some plus signs, a couple of them, but a majority of minus signs. So electrons from finger added to electroscope. Okay. The next frame said remove my hand. So that was cutting off the bridge. What was the arm like at that time? It was still vertical, meaning it's still a checkerboard pattern on the inside. It's neutral, plus minus minus plus, plus minus minus plus. And in reality, there are extra electrons up on this plate because the PVC pipe nearby is misleading them into thinking that there aren't enough electrons around. So there are extra electrons because of the positive charged rod nearby. Okay, so I'll say pathway for electron flow removed. And now, what is the final situation? There's no charged rod nearby. After I take the rod away, the extra electrons up here on the plate realize, whoa, we were misled the whole time. We thought that we were neutral, but in reality, we were being misled by the presence of this positive charge. Now that it is gone, I see all these extra electrons around me. Run away, get away from other electrons, like charges repel. So they spread out evenly everywhere. That means there's still some electrons extra left on the plate. But meanwhile, some of those electrons that had been up on the plate went inside onto the arm and tried to push the arm away from the bracket. So it's a crude method, but sorry, that's a minus sign. There are extra electrons spread throughout the electroscope. So electrons spread throughout the electroscope. Ha, you spell it. That is what happens. So here it is, real time, the replay. I touch the plate on the electroscope for a moment, making it neutral. I charge up the PVC pipe. No doubt you guys are going to turn this into a meme or something. And it's now positively charged. I bring it near the electroscope. The arm swings. I touch the bottom of the plate. I give it some electrons. I take away my finger. I take away and there it works. Okay, so good thing I didn't shut this off. This concludes this particular handout. The idea is, uh, what's the punchline? The punchline is the charge on this object is the opposite sign of the charge that I used to charge it. This is a positively charged PVC pipe. The electroscope now has extra electrons that really came from my finger during this demonstration. And now they're spread out there. So this is charging by grounding, is what the title of this handout says. I would also call it charging by induction, meaning I didn't directly touch this to that. In fact, let's make that a follow-on experiment we do right now. Okay, so I'm going to neutralize the electroscope, and I'm going to charge it up by scraping electrons off this PVC pipe. And now, unlike the instructions, I am going to directly touch the electroscope with the PVC pipe. And okay, it crudely shows this is now a demonstration of charging by conduction. When the charged object directly touches, what happens here is electrons transfer onto the PVC pipe. That's what they wanted to do in the first place. And it's more influenced, by this whole thing when it's near, but there's a little bit residual positive charge on the electroscope because some electrons actually made it onto the PVC pipe this time. So that is follow-on bonus feature to this video where I demonstrated charging by grounding, charging by induction for this entire handout, and then bonus feature charging by conduction. What's the difference? Now they both have the same sign charge. So in charging by conduction, this started off positive, it touched that, and so now electrons went there. Remember, it's always the electrons that move, not the positive charges. And leaving behind a net positive charge on this, but this thing wasn't completely neutralized. It's like, oh, it needed 1,000 electrons. This thing gave it 200. So this is weaker than this. This is weaker than it started, but overall, the same total charge on this. So if I'd scraped off a total of 100 electrons, then there's still a total of 100 electrons missing. Some of them here, the rest of them there. Now, I feel like I can conclude this video. All right, ciao.